Welcome to the second lecture of module 5. In the last lecture, we had a introduction on distillation. And then we discussed the equilibrium relationship T x y diagram and x y diagram. T x y and x y diagram. We have discussed the ideal relations like Raoult's law, and we have also discussed the relative volatility. In this lecture, we will discuss the deviation from ideality and the azeotropes. The most of the cases in general, the systems with equilibrium, we consider the equilibrium curves no inflection points. Now, if there is strong interaction physical or chemical, then the equilibrium curves looks different. In such a system where there is a strong interaction, physical or chemical, there is a critical composition where the liquid and vapor compositions are identical. Liquid and vapor composition are identical. In this case, separation cannot be done without changing pressure, and this mixture is known as azeotropes. So, this critical mixture where the liquid and vapor compositions are same and they are known as the azeotropes, and azeotropes means it boiled at constant pressure without change in composition. This is the azeotropic mixture. So, these azeotropes have two different types. One is called minimum minimum boiling azeotropes and second is maximum boiling azeotropes. Minimum boiling azeotropes, this is more common. Now, we can see two types, as we said, one is minimum boiling azeotropes and another is maximum boiling azeotropes. Now, a mixture with total pressure is greater than calculated from ideal law, calculated from ideal law. Then it shows the deviation from Raoult's law. That means, if it is greater, then the deviation will be positive. So, positive deviation from Raoult's law, and the partial pressure of components should be greater than the ideal. Now, if positive deviation is large, one, and second, vapor pressure difference of the two components are too large. We can see the total pressure curve P t versus x and P t versus y, total pressure curves passes through a maxima at certain liquid composition. If this is happened, total pressure curve passes through a maxima at a certain liquid concentration. This liquid mixture at this location is known as the constant boiling mixture, constant boiling mixture. As we can see at azeotropic point, where the total pressure curves, concentration curve reaches a maxima, and the corresponding to the concentration of x is equal to y, x equals to y. If we plot T x or T y, this should pass through minima. That is why This mixture is known as the minimum boiling azeotrope. Minimum boiling azeotrope. As we know, at this composition, a vapor compositions will be same as the liquid composition, and it will boils at this constant temperature without change in composition. So, this type of mixture cannot be separated by ordinary distillation. At that pressure. So, here x will be equal to y and alpha, the relative volatility will be 1. The azeotropic composition changes with pressure. In some cases, if we change the pressure, the azeotropism may be eliminated. The azeotropism may be eliminated. Now, this is positive deviation from ideality. Now, in some cases when the total pressure calculated for a system, total pressure is less than the ideal value. So, this is known as the negative deviation from Raoult's law. And in these cases, the partial pressure of the constituents, partial pressure of the constituents would be less than the ideal value. And the solution will approach ideality. Solution will approach ideal value when the concentration of the components approach 100%. So, these are the azeotropic points, and when negative deviation is large, negative deviation large, and second is vapor pressure difference between the components is not too high. Then the total pressure curve, versus composition curve pass through a minimum. Then the T x T y curve will pass through maxima. So, this is maximum boiling azeotropes. Maximum boiling azeotropes. So, maximum boiling azeotropes, as we said before, maximum boiling azeotropes are less common. Very well known examples are the HCl water mixture at 11.1 mole percent HCl at 110 degree centigrade temperature at 1 STD atmosphere, standard atmosphere pressure. So, now we will discuss another important equilibrium diagrams which is required for the distillation calculations is the enthalpy concentration diagram. In general, in a distillation calculation, we assume constant molal overflow, molal overflow for a distillation column design. But in actual there is variation of liquid and vapor flow rates, and which is depends on the enthalpies of the liquid and vapor mixtures. So, the limitations can be eliminated. So, if we use enthalpy balance with the material balance. So, this is the typical enthalpy concentration diagram shown over here, and here as we know during distillation, during the change in phase, the change in compositions occurs, change in composition changes the enthalpy. So, this is the binary vapor liquid equilibria plots for binary system. It is plotted as enthalpy versus concentration at constant pressure, and this will be very much useful in distillation calculation. Now, suppose at a given temperature, at temperature T and composition X. So, molar enthalpy of the mixture would be equal to sensible heat plus heat of mixing. And this we can calculate using HL would be equal to CL into TL minus T naught M average plus delta HS, where HL is the molar enthalpy at TL. TL is the bubble point corresponding to the liquid concentration, bubble point corresponding to the liquid concentration at that pressure. CL is the specific heat of solution, and this is energy per mole degree. T naught is the reference temperature, M average is the average molecular weight of the solution, and delta HS is the heat of solution, at the reference temperature T naught, and the concentration which is for the pure liquid components. So, delta HS is the heat of solutions. Now, this heat of solution we can calculate or we can obtain from some literature data. Now, if delta HS will be negative when heat is evolved during mixing, and the value will be 0 when it is ideal solution. The heat capacity in this case, heat capacity for ideal solution would be the weighted average of the pure components. Now, it is very difficult to find out the mixture values. Difficult to obtain. If we assume, we can get the approximate values. Assumptions. Assume unmixed liquids, mixed liquid are heated to the dew points, that is Tg, and second vaporized raised at Tg, and then vapor mixed. So, we can calculate Hv would be equal to Y into Cpa Ma TL minus T naught plus lambda A Ma plus 1 minus Y Cpb Mb Tg minus T naught plus lambda b Mb, where Cpa and Cpb, these are the specific heats of pure liquids A and B, and lambda A and lambda B, these are the latent heat of vaporizations of pure substance at Tg, latent heat of vaporization. Of pure substance at Tg. All these informations will be used to construct this enthalpy concentration diagrams. So, the enthalpy concentration diagrams is plotted at constant pressure, and each point on this enthalpy concentration diagrams, each point represents different temperature, and the upper curve, this one HVY curve, upper curve HV versus Y, it is a plot of saturated vapor enthalpy, saturated vapor enthalpy versus vapor composition, and the lower curve is the saturated liquid compositions curve HL versus X. HL is the saturated liquid enthalpy, and X is the liquid composition. Now, for any given composition, the difference between these two curves at any points, the difference between these two curves difference between the curve at a given composition is the latent heat of vaporization of the mixture, is known as the latent heat of vaporization of the mixture. Now, inside these two curves, inside this envelope is a two-phase mixture. Inside the two curves is two-phase mixture, and sometimes between these two curves constant temperature tie lines, between the vapor and liquid curves are provided. O and P one such tie lines, O, P one such tie lines. Now, the mixture beyond these 2 points, one is above this HVY curve is the superheated vapor, and below this curve is the subcooled liquid. So, above HV versus Y curve is the superheated vapor, and below this line is the subcooled liquid. Any point below this HLX curve. Now, there is a direct relations between the HXY curve with the XY curve, equilibrium diagram. So, if we have enthalpy concentration relationship, we can have direct relation between HXY and XY diagrams. Now, if we have tie lines which connects the equilibrium liquid and vapor composition for HXY diagram, then it will be easy to construct XY diagram. So, only the end points of the tie lines, end points of the tie lines is required to obtain XY diagram. Now, let us see, we have the equilibrium curve of HXY diagram. and point, we will just place the XY diagram below the HXY diagram. Now, start at the liquid compositions at point O, start at point O and draw a vertical line. Draw a vertical line. So, it will give the composition on the x axis, composition on the x axis at x O, it will be x O, composition on x axis would be on x O, and then draw a vertical line from the HV y curve, draw a vertical line from point P. It will intersect the diagonal line say at point Q, and from this point draw a horizontal line from point Q, draw a horizontal line so it will crosses a point at point G. So, the composition of this will be y p. So, this is the equilibrium point. Similarly, if we have other tie lines, similar way we can plot and we will obtain the equilibrium curve. Similarly, if we have the equilibrium curve, we can do in the reverse direction. We have the XY diagram. Then we can follow the reverse procedure to obtain the HXY diagram. Now, let us take two solutions at I and two solutions I and J. I represents I mole of a mixture of enthalpy H I and concentration Z I, and J mole of a mixture of enthalpy H j and concentration Z j. Now, the solutions I and J mixed adiabatically and produced a mixture K of enthalpy K mole of enthalpy H k and concentration Zk. Now, if we do the material balance, total material balance, I plus J would be equal to K, equation 1. Then the component balance, component A balance. So, I Z I plus J Z J would be equal to K Z K. Enthalpy balance, I, this is 2, I H I plus J H J is equal to K H K. Now, if we eliminate K from equation 2 and 1, what we will obtain? I by J would be equal to Z J minus Z K divided by Z K minus Z I. Similarly, if we eliminate K from equation 3 and 1, we obtain I by J would be equal to H J minus H K divided by H K minus H I. We can write from these two relations Z J minus Z K divided by Z K minus Z I would be equal to H J minus H K divided by H K minus H I. So, now from this we can write H K minus H I divided by Z K minus Z I would be equal to H J minus H K divided by Z J minus Z K. So, left hand side it gives the slope of I k line, and right hand side gives the slope of J k section, and so points I J k, these are collinear. So, point, that means point K is on the straight line I j. That means, if we remove J from a mixture K adiabatically, mixture I would result. Now, let us consider any points above the H V x curve, say point C and it will be useful if we consider this in terms of the saturated vapor and saturated liquid. So, consider C can be resolved by adiabatically removing saturated liquid that is at point E from saturated vapor F, and which is shown over here. This can also be considered removing adiabatically saturated liquid from G to G from I, G from I, or J from K, and any such combinations can be drawn and we can obtain C. Now, if we project all these lines, we can have the lower curve which is obtained over here at the bottom curve. Now, for any combination, for the combination F minus E equal to C, the material balance if we do, E by F would be Z C minus Y F by Z C minus X E. So, we can write line C F by line C E. This is the point with a slope is E by F, and it is drawn on the XY diagram, and also it meets at point x is equal to y is equal to Z C on the XY diagram on the 45-degree line. Similarly, other plots can be done by I by G and J by K. This is also shown over here, and this is drawn in the XY diagram. Three important observations we can see. One is, if H V y and H L x, these curves are straight lines, straight parallel curves, then the ratio E by F would be equal to G by I would be equal to J by K for adiabatic subtraction. Then the corresponding curve on x y would be a straight line. Now, second point is that if we moved upward, C moved upward, then the curve on x y will be steeper. Finally, will coincide with the 45-degree line when C is at infinity. And third point, we can see if C is on the HVY curve, then we can see the xy curve will be horizontal straight line, will be horizontal straight line, and C is on the HLX curve, then XY curve will be vertical straight line, vertical straight line. Thank you.